Hello guys, my name is Karthik. Today my topic of presentation is for decision trees which are widely used in machine learning. I will take you across through my presentation through various topics of decision trees. So what is the overview of my topic today? So initially we'll start with what is a decision tree and how to build it. What are examples of your sample decision trees? How to construct a decision tree, binary and non-binary trees, entropy, randomness, pruning trees, decision trees in gaming, and at the end we'll be taking off summary. Okay, so what is a decision tree? Okay, initially let's start with what are decisions. Decisions are what we take before doing any act. In a day, we take a minimum of 10,000 of decisions, whether to eat now, whether to sleep now, whether to go for playing now. All these are decisions. So this is what our mind is capable of, and what we do by taking a decision. But how interesting can we make it by extending this decision to a machine? Wonderful, right? So what this decision tree exactly means is that a machine has capability of taking decisions by providing it a set of data, which means that you given data to the machine, and it has capability to des- by it has capability to take a decision based on a previous or the data which we have been provided, which has been provided. So example, just imagine how wonderful it will be when a robot comes automatically and it takes a decision whether it has to sweep the house now without you even predict telling it to do so. By you have to just give it the data saying at this time every day I used to sweep, so now you have to sweep. So it means like that. So in technical terms, it is a predictive model based on branching series of Boolean tests. So what is a tree? You all know what is a tree, right? It starts with a root and then branch, then stem, then leaves. So it is the same thing here. So Boolean tests means it is yes or no, one bit 1 or bit 0, whether it is true or false. So in this, as a subpoint says, these smaller Boolean tests are less complex than one stage classifier. Imagine a single change rather than a divided chain. A divided chain is much easy to interpret, right? So that is what is a simple decision tree. It is a model of branching. Okay, like how a tree looks, but it is an example of an inverted tree. So let's look at a sample decision tree, what they look like. It works like a flow chart. Many a times while studying you would have made a flow chart, right? So it looks exactly like that. It has a parent, and from that there are nodes branching out. So as I said earlier, it looks like an upside down tree, and it has nodes. Nodes are either each child of the parent class. So it is represented either in a circle or a rectangle, and it each node represents a test or a decision, uh, either I should do this work now or no, either I should whether am I eligible for something or no. So and what do the lines of the branches depict? They depict an outcome. They connect the they the lines of branches connect the nodes such that the decision is complete. Now, what do you mean by circles in the terminal? So they represent the leaf nodes. And what is the top or starting node called as? It is known as a root node. As you know, commonly in a example for a tree, the basic starting point is a root. So in the same way, even for the machine learning, even for the decision tree, it is known as a root. And the internal nodes are represented again by rectangles. So here is a simple example of here is a simple example of a decision the decision tree. So what it says is initially the parent node or the root node is the age. So it this model is used to predict whether of given an age, it is to predict whether a person has a personal computer or no. So as simple as that. So you provide the data saying if the person is lesser or equal to 30, there are two possibilities. He's a student and he might have a personal computer, or he might not have a personal computer. And what about from the ages 31 to 40? It's saying that we are providing a data that yes, from 31 to 40, all people have a like they buy a computer. And what about age greater than 40? If suppose their credit rating is excellent, then they don't buy a PC. Whereas if their credit rating is fair, then they buy a PC. Another example is bank loan. Many times people go apply for a loan, right? How do the bank systems evaluate whether a person is eligible or no? This can be made easy for by using a decision tree. What it does is there are few like what is the main classification for whether a person is eligible for the loan or no? One is approved class, one is denied class. So in the approved class, the people who are to be approved are given a set of criterion. For example, in the for example, for a person to be approved for a loan, he should, as stated here, the borrower has good credit history, in the sense the credit rating is in excess of some threshold. They set a remark. Then if suppose the loan amount is less than a percentage, less than some percent of collateral, example, if your house value is around 10 lakhs, and if you are purchasing a loan of around 15 lakhs, then it is a good value, saying that collateral is almost reaching out to the amount you are purchasing. And the third option is the borrower has a particular income, so that he can pay back the loan in very regularly. And here in this case there are three possible, like 3 into 3 power 3, like around um, many possible scenarios, where it says that it's actually it should be 3 power 2 there. So it should be around 9 scenarios. And if suppose the possibility, if the parameters are splitting, the nodes can be adjusted, and the scenario grows exponentially. Now, so what can we what can we say from this? In the decision tree, we made a series of Boolean decisions and followed the corresponding branch. So we started with age, then we followed the line and reached out to age if suppose it's less than or equal to 30 years. So at the end, we are able to answer yes or no questions for each of the application we want, either is applicable, whether the person is eligible for the loan, or whether um, like a person buys a PC, or example some, and it goes on, like lots of applications of decision trees in the real world applications. So what do like actually do we have an alternative for decision tree, or why is decision tree preferred among other all algorithms? So here I'm just here to depict a small example. So if we have a example saying to predict whether a person is going to be stuck in traffic at so and so time. So we are not representing this graphically, but we are representing it as a code. If hour equals 8 a.m., then commute time is long, or rather the person has to wait for a long time. Or if suppose the person is like if he leaves at 9 a.m., or if there is an accident, then commute time is long. So you need to specify each and every set of rules. Whereas in this case, you can notice that all attributes do not have not been used in each path of decision. Like even all attributes may not even appear in the tree. So a decision tree is much better than such algorithms, because you don't need to provide each and every data to be specific. You can provide a small, like you can provide a randomized data, and it takes a decision tree on its own, the algorithm of the decision tree. So how to create a decision tree? That's a basic fundamental, right, of what we talked today. So we first make a list of attributes that we can measure. That is, uh, whether a person has a good credit score for applying for a loan, or whether the person is having a very good income. Then we choose a target attribute. The target attribute in our case is whether the person is eligible for the loan, or whether a person buys a robot today, or whether a person buys a PC today. All these things are part of the target attribute we want to predict. Then we create an experience table that lists out the different data that we have been predicting over a previous time. And then it's part of the algorithm to decide on whether by taking the maximum probability of what is the outcome to be decided upon. Then how do we choose the attributes? The basic structure of creating a decision tree is the same as most of the decision algorithms. The difference lies in how we select the attributes for the tree. An example of algorithm is ID3, which was invented by, as you can see, Ross Quinlan in 1975. So how do we choose the attributes from where we left in the previous video? The basic structure of creating a decision tree is same for most. ID3, as I stated, is one algorithm for making a good decision tree. But decision trees can be classified into binary trees and non-binary trees. What are binary trees? So here is a diagram of a simple binary tree. Each binary tree, the parent node is should be divided, should have two parent and the child nodes. That is, for example, here you can see that the parent node 1 has two child nodes 2 and 3, and in fact again 2 is split into 4 and 5. And this is an example of incomplete binary tree because the parent 6 does not have any child, two children. It has only one child node. So here is a perfect binary tree. Example A is a perfect binary tree. As you can see in example B, the perfect binary tree, it's not a perfect binary tree because node C has only one child, whereas in example 3 it's not equal because all the nodes are of not of same level. So characteristics of a binary tree is two branches leave each non-terminal node. As you can see, like one had 2 and 3. So those two branches cover outcomes of the test state, whether yes or no, true or false. Exactly one branch enters each non-root node. Non-root in the sense which are apart from the root node, everything else is termed as a non-root node. There are n terminal nodes. Now let's talk about non-binary trees. In the binary tree, with as compared to a binary tree is a it states that every parent should have two children, two child nodes. Whereas in non-binary tree, that is not the case. Two or more branches leave each non-terminal node, as it stated here, and those two branches cover outcomes of the test. And there are n terminal nodes in a non-binary tree. So in the case 1 it's a non full binary tree, whereas in the case 2 it's full binary tree. What is the goal? Dual goal. We have what is the goal of creating an algorithm or a decision tree? So we develop a decision tree which should be small, in the sense which is interpretable, which is easy to understand, and which does not which is less susceptible to overfitting. And the second is it classifies and predicts class with accuracy. There should be no source of error, and if there is a source of error, the machine is having a high chance of predicting something which you don't want. So that is obviously what we don't prefer, right? So we develop a decision tree which classifies and predicts everything with good accuracy. What is entropy? Entropy is something of randomness. Randomness in the sense of what? If suppose we if suppose let's take an example of saying distribution of some table. Suppose you say in all the states in India the population is same, so that is known as entropy is being zero or randomness is zero. Or if suppose um, there are lots of variations in the population population distribution, then then the entropy is maximized or the randomness is maximized. The next topic what will be or okay then here is a formula for entropy which we will not be discussing in detail. You can just have a look at it. So it's nothing but the summation from I equals 1 to some n set of examples. Okay, now for making the decision tree small we need something, right? So that is known as pruning trees. This is a technique of reducing the number of attributes in a tree. Two types of pruning. One type of pruning is pre pruning and other is post pruning. Each has its own advantage. In pre pruning we decide during the building of the process to either we have to stop or keep adding the attributes. However, this is a problematic. Do you know why? Yeah, so here is this problem. Sometimes attributes individually do not contribute to the problem or the decision. Each all together might contribute to the decision. So adding individually might become a problem. So that is known as pre-pruning. Excuse me. So what is post-pruning? Post-pruning waits until the full decision tree has been built and then prunes the attributes. So this is a solution to the pre-pruning, right? So it has the capability of taking the decision at the end of the at the end when it's a collective income, collective input. There are two techniques of post pruning. One is subtree replacement and one is subtree raising, which we will not be discussing in detail. You can just look into, you can just Google about that. Okay, so as we talked about ID3 algorithm, how is it used in gaming? So example, let's say a chess game is built and a chess game is designed and it needs to predict the player's next move. So by playing continuously with the user, it keeps predicting whether the person's next move is going to be what and how to make him lose. So in this case, ID3 is very famous in gaming industry especially. This is another example of whether a game is going to like be defense or it's going to be acting as an attack. Okay, what is like we at the end when we summarize, decision trees can be used to help to predict the future. It predicts whether everything is what we want. It takes a decision of its own. It has a capability of taking a decision of its own. Then the decision tree, and these trees are very easy to understand by any machine. Decision trees work more efficiently with discrete attributes or with yes or no, bit 0 or bit 1. They work good with discrete attributes. And these trees may suffer from error propagation if suppose we provide some error in the data or something like that. So this is the end of this topic.